Let's take a look at 4.6 exercise 7, calculator active. The velocity of a particle moving along the x-axis is modeled by a differentiable function, v, where the position x is measured in meters and time t is measured in seconds. Selected values of v of t are given in the table above. Alright, from the get-go, this problem gives us a lot of important information. First, it tells us that we're working with a moving particle. So since we're working with this particle that's moving around this x-axis, we know that we're probably going to be working with position functions, velocity functions, and acceleration functions potentially. And then it gives us this table. The way we can think about this table is essentially a snapshot of the velocity function for this particle. What this means is that instead of giving us a full fleshed out graph or a full function, it's giving us snapshots, where it gives us particular points in time and the particle's velocity at that point in time. The final piece of information it gives us is the initial condition. So if we say that the position function is x of t, we can say that x of 0 at t equals 0 seconds is equal to 7 meters, since the initial condition at t equals 0 is x equals 7. Time-wise in the exam, you probably don't need to do this, but I've written out the information that you need in this problem, or what it's given us so far. We have a table, a snapshot of the velocity function for different values of t. We have the initial condition, x of 0 equals 7, and then finally, we know that with this particle, it gives us a velocity function. But really, that velocity function is telling us x prime of t. It's telling us the slope, or how fast the position is changing. Given this information, let's look at the question. Estimate the acceleration of the particle at t equals 36 seconds. Show the computations that lead to your answer, indicate units of measure. Immediately we know that we're going to be looking at acceleration, which is how fast the velocity function is changing. In other words, v prime of t. You can also think of this as x double prime of t. But since we have information about v of t, that's what we're going to be focusing on. In particular, we're going to be looking for where t equals 36. So we're looking at the acceleration at 36 seconds. If we plug that in, that's v prime of 36. Now, we don't actually get given v prime. So what we're going to do is we're going to use an approximation method. Notice that t equals 36 seconds is not actually one of the values that's given, but rather it's in the middle. It's the midpoint between these two timestamps, 32 seconds and 40 seconds. Now, to build some motivation on why we care to approximate or why we need to, let's just take a typical graph, a normal curve in the first quadrant. And right now our goal is to find v prime. So if this is v of t, what we're trying to do is we're going to try to find the instantaneous slope, the instantaneous rate of change at 36 seconds. But here's the thing, we don't actually have v prime of 36. So to approximate this slope, we're going to take the two nearby points and get the secant slope. By calculating the secant slope, we're going to get the approximate instantaneous slope. It might not be perfect, it probably isn't, but it's a good way to approximate. In theory, this instantaneous slope is when this secant slope gets infinitely closer to this point. That being said, the way we're going to approximate this is change in v of t over change in t. The reason for this is because the normal slope formula, rise over run, or change in y over change in x. That's going to be equal to v of 40 minus v of 32 over change in t, which is 40 minus 32. And what we're going to get is we're going to plug in v of 40, which is 7 minus negative 4 over 40 minus 32. You'll get 11 over 8. The final part of this question is to indicate the units of measure. Some of you may know already that this is going to be meters over seconds squared, but if you want to know why this is, what we can do is we can take a look at this section. We know that v of t is in meters per second, or meters over second as given here. So what we're doing here is we're going to do meters over seconds divided by t, which is in seconds again. And then if we multiply that by 1, or s over s, we're going to see that these cancel, and you get meters over second squared. Thus, the particle's acceleration at t equals 36 seconds is approximately 11 over 8 meters over second squared.